Hi everyone and welcome to our Advancing Sustainability Through Solar Generation project that are being tasked to us as a student from BEEI 2.3.6.4. Electrical Technology. We are comprising of 3 team members naming as Ridwan, Faiz and last but not least Anna. Stay tuned and we will walk you through our project overview.
Moving on to the executive summary. This proposal outlines the implementation of a solar generation project aimed at harnessing clean renewable energy to contribute to the region's power supply. The project emphasizes sustainability, environmental responsibility, and long-term energy cost savings.
Moving on, Malaysia is still new into renewable energy, but we have quite a few places which can be turned into a solar farm.
Based on our research, prospect location at Mukim Tanjung 12, Sepang, Selangor, was chosen for optimal sunlight exposure and minimal environmental impact, which can generate electricity with a capacity 50 megawatt, tailored to meet the energy needs of the community while allowing for future scalability.
The objective of clean energy sources, such as solar energy, is to address various environmental, economic, and social challenges associated with traditional, fossil fuel-based energy sources. Some key objectives of promoting and adopting clean energy like solar power such as environmental sustainability, climate change mitigation, energy independence, economic development which can foster the growth of the clean energy industry, creating jobs and stimulating economic development, energy affordability to improve energy affordability by tapping into abundant, free sunlight to generate electricity, and the list kept going down. But by pursuing these objectives, societies aim to transition to a more sustainable, resilient, and environmentally friendly energy system, with solar power playing a crucial role in achieving these goals.
Moving on, I'll start by explaining the simulation circuit created by MATLAB Simulink to simulate on what's actually going on inside a solar panel when producing the electrical current. First and foremost, to generate an electrical current using the sun's rays are attenuated as they pass through the atmosphere, leaving maximum normal surface irradiance at sea level on a clear day at around 1000 W per square meter. The minimum solar insolation needed to generate electricity is 100 to 200 with M2, which is enough to power at least one lamp and fan.
In the simulation, we are using input of 1500 solar irradiance at 25 degrees Celsius.
By using this input, we can mimic the output voltage, which can be observed by using voltage measurement component through scope 1.
At the same moments, an RLC resistor inductance capacitor circuit is formed by using an inductor as a load for the solar cell.
The capacitance of the solar cell is found by measuring the frequency of the damped oscillation that occurs at the moment of connecting the inductor to the solar cell.
IGBTs, insulated gate bipolar transistors, and diodes play crucial roles in solar power generation systems. IGBTs are utilized in inverters to convert DC power generated by solar panels into AC power, while diodes are employed for preventing reverse current flow, ensuring efficient energy harvesting in photovoltaic arrays. Pulse generators in solar power systems control the switching of power electronic devices like IGBTs, enabling precise modulation of pulse, width modulation, PWM signals in inverters. This facilitates the efficient conversion of solar-generated DC power to AC power, optimizing energy output for grid integration. RL resistor inductor capacitor circuits in solar generation serve as filters and impedance matching components, enhancing power quality and stability in photovoltaic systems. These elements help manage and mitigate fluctuations in electrical signals, contributing to the reliability and efficiency of solar energy conversion. Pulse width modulation. PWM generators in solar power systems control the switching of power electronic devices, such as IGBTs, by varying the width of pulses in the generated waveform. This modulation optimizes the efficiency of power conversion, allowing precise control over the output voltage. Universal bridge. Inverter functions in solar generation systems, then take the modulated DC power from solar panels and convert it into AC power for grid compatibility, facilitating the integration of solar energy into the electrical grid. The combination of PWM generators and universal bridge inverters ensures a reliable and efficient transformation of solar-generated power for practical use.
Hello, my name is Faze, and as my colleague explained, when the inverter output is directly connected to the resistor, which is the load side, the oscilloscope will display a square wave.
Even yet, the 240-volt AC isn't smooth enough to be classified as a sinusoidal wave. We must add the passive filter, which consists of the inductor and capacitor, to smooth it out. We can obtain the pure alternating current waveform, or sinusoidal wave, by adding the passive filter. Thus, after applying the passive filter, you can observe that the pure AC waveform is on the right-hand side of these two scopes. Additionally, you can observe the DC waveform on the left-hand side, which is 110 to 120 DC volts that are being generated from the solar panel. So the pure AC is what we needed for supplying the power to the home.
In conclusion, the utilization of solar energy represents a pivotal and transformative step towards a more sustainable and environmentally conscious future. As we confront the challenges of climate change, resource depletion, and energy security, solar power emerges as a clean, abundant, and renewable solution with numerous benefits. Solar energy helps mitigate the impact of climate change by reducing greenhouse gas emissions, offering a crucial alternative to fossil fuel-dependent energy systems. The economic advantages of solar energy are evident in job creation, technological innovation, and increased energy independence, fostering economic development and resilience. Moreover, the affordability and accessibility of solar power contribute to energy equity, allowing communities, both urban and rural, to gain reliable access to electricity. The decentralization of energy production through solar installations promotes resilience in the face of natural disasters and reduces the vulnerability of centralized power grids. The long-term sustainability of solar energy, coupled with ongoing advancements in technology and decreasing costs, positions it as a key player in the global energy landscape. By embracing solar power, we not only address immediate environmental concerns but also pave the way for a more sustainable, inclusive, and secure energy future for generations to come. In essence, the adoption of solar energy represents a commitment to cleaner, greener, and more resilient societies. As we harness the power of the sun, we take a significant stride towards achieving a harmonious balance between our energy needs and the preservation of our planet.